In this lecture, I'm going to talk a little bit more about the sun and what the conditions have to be like in order for nuclear fusion to take place, the way we talked about in the last lecture. You probably can't read all of the writing on this diagram, but this is a picture of the sun with part of it cut away. The outside part here is an actual photograph. And you can see there's different layers within the sun. We're interested in what's going on in the core. The core is where the nuclear fusion is taking place. In the outer parts of the sun, there is no fusion. All of the fusion is happening down in the core, and then the energy makes its way outward through various processes and eventually goes into space and eventually gets to us. So the core is the part of the sun at the very center where fusion is taking place. That's how the core is defined, as it's the part where the conditions are right for fusion to happen. It turns out that you need some very particular conditions in the core in order to get nuclear fusion to happen. Nuclear fusion is very difficult to get going. This is why we don't use it in everyday life to make electrical energy for us to use on Earth, for instance. It's because it's very difficult to get it to happen. The problem is that what you're trying to do when you're fusing hydrogen into helium is you're trying to stick two protons together. That's the fundamental thing that we're starting with, is we're trying to stick two protons together. But there's a problem with that because protons both have positive electrical charge. And we should remember from physics that if we have two things that have like charges, they repel. Opposites attract and like charges repel. So two protons do not want to be pushed together. It's like if you have two magnets and you try to push them together and you can't get them to go together, they push back, they push you away. Protons are going to do that too. They do not want to be pushed together. And so something has to force them to get so close together that another force will take over and allow them to join in spite of the electrical repulsion. There's another force called the strong nuclear force. And it's called the strong nuclear force because it's about the strongest force in the universe. It's ridiculously strong. It just only happens in the nuclei of atoms. That's why we don't see it in everyday life. If you can get the protons close enough together that the strong nuclear force can take over, then you can get them to fuse. But you have to get them close enough together. So there's two things that can do that. One is just by it being extremely dense. If you have lots and lots and lots of atoms crammed together in a very, very, very small space, well, then you are going to be much more likely to get the protons close enough to overcome the electrical force. The other thing that helps is temperature. High temperature will help this because high temperature means that the particles are moving around very, very fast. Temperature is a measure of kinetic energy. The more temperature you've got, the more kinetic energy you've got. That means they're moving very, very, very fast. And so if they're moving around ridiculously fast, then they're going to have high-speed collisions. And if they're going fast enough, you can get that collision to happen fast enough where the electrical repulsion of the protons is not going to push them back apart. So if you push them fast enough and hard enough, you can get them to fuse. So what kind of conditions do you need? Well, just for example, at the center of the sun, the temperature is 15 million Kelvin. The outside of the sun is 6,000 Kelvin. So when we're talking about a very, very, very high temperature in the core, 15 million degrees is very, very, very hot. And it's also ridiculously dense. I don't have a specific number to give you on that one, but it's very, very dense in the core of the sun as well. Very much outside the realm of everyday experience. Now, when you get this, a certain kind of condition applies. And this is a very, very important concept because what I'm about to talk about is what drives the evolution of stars, what makes them change over the course of their lives. So this is a very important vocabulary term for you. you'll see two different words used. One is hydrostatic equilibrium. That's what most professional astronomers call it, and that's what my tendency is to call it. Your book refers to gravitational equilibrium because that makes more sense in terms of what's going on. It helps you think about what's going on in the situation a little bit better than some word like hydrostatic that you don't know what that means. The key thing is that it's an equilibrium. Equilibrium means balance. And this is going to be a balance between two forces. Inside a star, you've got two main forces going on. One is gravity. Gravity is trying to collapse the star. It's trying to push it inwards. Gravity tries to pull things together. That's all that gravity ever does, is it tries to pull things together. So gravity is trying to make the star collapse. But there's another force at work that's preventing that. We know that there has to be another force, because if there weren't another force, then gravity would take over, it would make it collapse, and the sun would be changing size. And the sun is not changing size. We know that. We have observed it. We know that the sun is not changing size. So what is this other force? Well, the other force is gas pressure. This is the pressure you learned about in chemistry when you studied ideal gases. Whenever you heat something up, there's an outward pressure that pushes outside and is higher the hotter the temperature is. So it's the pressure that makes a balloon blow up, for instance. So gas pressure that comes from the fact that the interior is ridiculously hot, that's what's going to balance the gravity. So gas pressure is trying to make it expand. Hot gases expand. You remember this from chemistry, that hot gases expand. So gas pressure is trying to make the star expand. Gravity is trying to make the star collapse. When these two things are equal, which is the case most of the time in stars, then we say the star is in hydrostatic equilibrium, or gravitational equilibrium if you like your book's word better. If these things are not equal, then the size of the star will change. Let's say for some reason gravity is bigger than the gas pressure. If that's the case, then gravity is going to cause the star to collapse and the radius will decrease. If for some reason the gas pressure is bigger than gravity, then that causes an outward force and the star will expand. So how could that happen? Well, let's say for some reason that the rate of fusion increased. If the rate of fusion increased, then it would get hotter inside the sun, and that would mean the gas pressure would get bigger. It might overcome the gravity and push it out a little bit. Or let's say the rate of fusion decreased for some reason. If that's the case, then now gravity is going to be stronger than the gas pressure, and that's going to make the star collapse. You end up back in an equilibrium because let's suppose, again, let's say that gravity causes the star to collapse. Well, if gravity makes the star collapse, then the temperature and the density in the interior are going to get bigger because you're cramming the same stuff into a smaller space. And so that's going to make the rate of fusion increase. Well, if the rate of fusion increases, then you're making more energy, you're making more heat. So gas pressure is going to increase, and it's going to push outward, and it's going to push the star back to the size it was before the gravity collapsed it. So these two things are always working against each other and always trying to make the star balance. At a certain point, they're not going to be able to do that anymore. There won't be a balance, and then we'll start to see some significant changes in the stars.